This is the part 2 video podcast for chapter 15 about field methods for lakes and estuaries. And now we're going to switch to estuaries. And again, many of the things that are in lakes can be used in estuaries and vice versa. But as I've tried to emphasize all quarter, where you sample, how you sample, what you sample is strongly influenced by the processes that are present in the local setting. So that's why I'm putting an emphasis on being aware of different settings and thinking about the field methods in that context. Okay, so when it comes to estuaries, the first thing is to simply know what it is. And if you haven't been introduced to these concepts, then let me just quickly go through a few of these. Of course, an estuary is where a river meets the sea. Very simple. And we can also give a little bit more technical, but still simple definition that we have a semi-enclosed water body with a salinity gradient. Now, there are longer definitions, but using a salinity gradient also essentially assumes that if you're making a salinity transition, you probably also have the process of tides present, because tides occur in the world's oceans and they're transmitted up into estuaries. We're not going to go into tides in detail in this course, so if you haven't heard about that before, I'm not going to address that here. I do have a whole video podcast from my HYD 143 class if you want to see more about that, or if you already took the class, then you know that. So when we talk about a salinity gradient, we're talking about the ocean having a salinity of typically 30 to 35 parts per thousand, and then the fresh water being less than half a part per thousand. And so we have a gradient. Haline means essentially salt related, so oligo, meso, and polyhaline in that order, going from lowest to highest salinity. So when the salinity is less than 0.5 parts per thousand, which you should be able to turn into parts per hundred, right? No problem. Okay, that's called the tidal freshwater zone. And that reflects the fact that tides propagate as a wave much farther upstream than how far salinity goes. There are many different ways to classify landforms in the environment or processes in the environment. And so let me show you a few as they relate to estuaries. The first is a geomorphic or landform-based classification. And here we're going to look at the role of the relief, like the range from lowest to highest elevations, the overall shape that is governed by the longer-term processes that are present there. And so, for example, in very high relief terrains that are also heavily influenced by glaciers, then we have what are called fjords. So a fjord is a place where the river meets the sea, where there is a river valley, but that's cut deeply into a high relief mountain basin. In contrast to that, if you keep in a glaciated environment, but you go from mountainous terrain to more gently rolling hills or lowland terrain, then you have what we call a fjord. So you probably have heard of a fjord, and you probably have not heard of a fjord, but nevertheless, here it is. And so it's just a low gradient, rocky glaciated system. Then if we go out of the glaciated setting, but go back to the high mountain kind of conditions, or at least high relief hills, then we have what are called rias. These are very common in Spain, hence the name. And if we come to a very lowland, like alluvial coastal plain setting, then you have, we just call the coastal plain type of funnel-shaped estuary. Again, you can see with all four of these examples, we have a river like really dominated by the presence of a large valley, a large stream network, in this case just not shown with a lot of tributaries, but basically a very well discernible river that's transitioning to the ocean. And, RIA, we're just drowning that out. All these, they're just drowning it out because sea level in the ocean is going up and down, by 100+ meters over tens of thousands of years. So we're drowning that and then emerging it and so forth. With the coastal plain type, there may be more of a funnel to that. I mean, this image here looks like the classic Delaware estuary, but other ones have much more of a traditional river network dendritic pattern to them. They just are lowland settings. Here in California, we have a lot of bar-built estuaries and blind estuaries. This is a case where the river drops out of the mountains fairly quickly, and you have very strong wave processes in the ocean presenting longshore transport of sand that can then block that off. Depending on the relative ratio of wave power to river discharge, then you can either have that perennially open as a bar-built estuary, or it could even get fully closed or seasonally closed as a blind estuary. If you have a very large delta, so very high sediment load pushing out from a river into the ocean, then you're not going to have an inland estuary as shown in the top 6 examples. Instead, you're going to be pushing out and having these fingers of channels delivering sediment out into what's called like a bird's foot looking unit or a delta. So there's different kinds of delta fronts, but it's generally protruding out into the ocean. And then lastly, you could have a tectonic setting in which you have a mountainous area. There may even be a ria, but that inland there's a larger lagoon isolated from the ocean and separated by some sort of connecting channelway. And then there could be deltas or other features like estuaries inland. So this is a landform dominated classification. You can see the role of glacial versus non-glacial, high terrain versus low terrain, relative river versus wave or tidal energy in the system. It's important to appreciate also that being mountainous or not mountainous is not just a descriptive phenomenon, but it relates to the relative long-term, when I say long-term, I mean hundreds of thousands of years of balance between tectonic uplift versus climate-driven landscape erosion. And that gets beyond the range of this class, but it's not just entirely descriptive or arbitrary when these classifications were made. From a different perspective, we can look at the processes that are taking place in the water and recognize 3 fundamental drivers. The river flow, where discharge may be, is going to be associated with whatever the natural flow regime is for that river. Tidal energy, tides are the hourly, daily, seasonally, monthly changing water levels that are taking place in an estuary, driven by interactions between the sun, the earth, and moon. See, I can't help myself. Now I'm defining what tides are. But in any case, there are undulations in the water surface associated with those astronomical phenomenon. And then waves, where you typically have wind or pressure gradients in the atmosphere, which also produce wind, causing surface waves and driving energy and changes to the land that way. So depending on the relative magnitudes of those 3, then you can have different landforms, some of which are named here. And if you put these names into Google or another web browser, you'll find example photos. I tried to put photos in here, but it just gets too busy, and I don't think it's very helpful. We're going to go visit some of these, particularly some tide-dominated estuaries, because that's what we have where we are. You could also add another dimension to this, which could either be the grain size of the material coming in, like if you're in a steep, glacially dominated area versus a coastal plain with basically mud, then how this plays out would vary. And you could also add another dimension here in terms of time. So how systems evolve through time, then they're going to change in their relative proportion of energy. Here's some examples of these systems. Chesapeake Bay is a classic coastal plain, flooded river valley. The overall main bay shows the funnel shape, but there are also many sub-estuaries, as we term it, related to the different large, medium, and small rivers entering the bay. High salinity near the mouth, low salinity at the heads of all of the tributaries and the head of the bay where the Susquehanna River comes in. The Mississippi Delta protruding into the Gulf of Mexico is an example of a delta setting. And then San Francisco Bay is an example of a tectonic-dominated estuary with inland, areas of lagoons, and then ria sorts of areas that are separating those or separating them from the ocean. Now I want to show you the details of the processes that are taking place and the associated landforms that result for the three different kinds of wave, tide, or river-dominated estuaries. So in the first example, we're going to have the schematic at the bottom, which goes from the river-dominated end on the right to the ocean-dominated end on the left. And in this example, if we look at the top graph, we have the energy going from 0 to 100%, the relative energy of waves, tides, and river processes. So at the upper end, the river is going to be coming in, and you might have a slope break or a sudden expansion to the river that denotes the onset of the estuary, or you might not have that at all. But you're going to have river-dominated regime with very minimal tides and no ocean-created waves. And at that end, you're going to see some kind of deposition of sediment as the velocity slows down, and we have this increase in cross-sectional area, so that will create some sort of bayhead delta or something like that. At the other end of the spectrum, in a scenario where there's very little tidal currents taking place, and you have a very strong wave regime, then that wave energy is going to bring in what's called longshore transport. That's where sand is moving along the coast, and it hits this opening and it just moves right across that, and it starts to fill it in. You can see that some of that sand is pushed in and out by the tide, so there might be a little bit of what's called the flood tide delta. That's when water is flooding into the estuary, which may be a little confusing to you, whereas opposed to like ebb tide is when it would be going out. So some of this material may be coming in, but the main landform is the barrier that's created by the waves. So there may be, this may change seasonally or just depends on the river regime, but typically you have a relatively low, diminishing river input, a central basin with just overall low energy, a relatively quiet lagoon, and then you have the wave-dominated barrier. Okay, now a tide-dominated estuary looks dramatically different, as you can see in these images. Here, we can have very strong river input coming in, but the river is able to carry itself all the way through quite a bit farther because there's no waves that are blocking off the mouth. And instead, we have very strong tidal energies. That's going to take the coastal sands from the longshore transport and redistribute them instead of across the estuary into these bars aligned with the estuary. So what that means now is that you have sand and mud that's being transported by the river and sand that's coming in from the open ocean, and those are all going to be redistributed primarily by the tides. So instead of having a delta formed by the river, those delta sediments are being smeared around by a channel network to create salt marshes that will grade from fairly muddy, especially muddy in the distal areas, and then more sandy along the channels where there are both river and coastal sands. So already, just considering these two examples, you can see the dramatic differences in landforms that are present in a wave-dominated estuary from a tide-dominated estuary. That means that if you're going to do a water balance, or if you're going to do water quality monitoring, or you want to know about the changes to a system like this through time, you have to come up with completely different approaches to how you're going to monitor. And there isn't the river end member example would be if you have like low tides and low waves, you would just be pushing out and having a delta just like you see in the Mississippi River case. Okay, so here's an example from Chesapeake Bay, and now I'm going to show more of a kind of a case study of monitoring for water quality and the overall health of Chesapeake Bay. So in Chesapeake Bay, we have seasonal changes to the salinity because we have the spring hydrological, we have the annual hydrological cycle, which in the spring brings a lot of fresh water pushing out all of the tributaries, pushing salinity out, whereas in the fall, after all of that is done and we're just into the regular rainfall regime, then you have a higher salinity pushing up into the bay. Estuarine water quality issues are heavily influenced by the fact that human civilization is disproportionately in the coastal zone and around estuaries, taking advantage of all of the food and other industrial applications that can take advantage of the estuarine setting. So, of course, you're going to have a very complex regime of land runoff and municipal waste discharge right into the estuary. Atmospheric deposition is something that we've learned more recently is a major contributor to nutrient pollution in estuaries. And then we see also the effects of eutrophication that are taking place, loss of submerged aquatic vegetation. So there's a lot of water quality issues that come into play. And as a result of that, since 1985, there's been the Chesapeake Bay Program. Now, here's a map of Chesapeake Bay. This is the largest estuary in North America, and it's shown here in this pale yellow. What you can see overlaid on that are all kinds of dots for different kinds of monitoring taking place, like fish index of biotic integrity, discharge measurements, ecosystem processes, benthic observations, nutrient observations, phytoplankton, zooplankton, water quality, and then the coverage of bay grasses. Why are they doing all this? Well, they want to preserve and improve conditions in the bay. And to do that, their goal is to characterize the baseline condition and see if there are changes in water quality through time and space. Look at the processes that link water quality and then the living resources. So, if we were to improve water quality, would we expect to see a benefit to the different organisms that are there? That's something you have to monitor. There are computer models that help us understand the system, so we need to calibrate and verify those, and then characterize habitat requirements. You can see in this program are many of the different kinds of monitoring that we're interested in, when I presented the different kinds of field research. We've got model calibration and testing. We've got just measuring and monitoring campaigns. There could be a before and after, looking at like when different treatments or storms come in or changes to dam operations, for example. The weird thing, though, is when you look at this map, it doesn't look like a very sensible way of doing things. Of course, there's a huge amount of focus on the tributaries. So here's the Patuxent River, and look at all these tributaries that have just this enormous amount of sampling taking place, whereas there's relatively little being done in the main bay itself. Of course, it's very expensive to do a monitoring program of this scope, and also, it's being done over time with changing politics and changing understanding, and so therefore the pattern that you see here is going to be changing through time. But it just shows some of the real-world challenges of designing an experiment to look at a large system like this to meet many different purposes. If we look at the system as a whole, the problems are driven by the fact that we have nutrients like nitrogen and phosphorus and sediments coming into the bay, as well as just loss of habitat from overwhelming amounts of sediment filling in tributaries or snuffing out the beds, increasing the turbidity in the water column, and so forth. And so this shows that for nitrogen is the bar on the left, phosphorus in the middle, and sediment on the right. You can see that in the Chesapeake Bay region, that croplands are the largest producers of nutrients and sediment, second by urban, suburban, then pasture, and forest producing the least. So there are goals that were established by the Chesapeake Bay Program to reduce pollution inputs to the bay. That was set in 1985 to be accomplished by the year 2000. However, that wasn't accomplished, and so if we look at nitrogen, here by around 2008, 47% of the nitrogen goal was achieved. For phosphorus, 63%, and for sediment, 64%. I'm not sure why these say nitrogen, but given these other, they should say phosphorus and sediment. But anyway, you could also see that really by 2000, it kind of had reached a peak, and it's sort of leveled off again, although not as much for nitrogen and sediment. So it's, you can set a goal and you can try to change society, and great progress was made as illustrated here, but it hasn't been fully successful yet. Let's look at another example. Here, if we look at the top, we've got nitrogen load reaching Chesapeake Bay, and we've got the river flow as the blue bars going to the right y-axis, and then we've got the load of nitrogen going to the left axis. Millions of pounds of nitrogen coming in as a result of human activities primarily. And you can see that these two lines mimic each other almost perfectly, because load is controlled by discharge. The same is true for phosphorus, but not quite as much. It's a little bit different because phosphorus isn't always dissolved, but there's a very high sediment constituent, and so unless you have enough water to move sediment, then the processes are just more complicated. However, they are related. So these goals have been set for a wide variety of aspects of ecosystem health for the estuary. Here's water quality. Like 16% of a recovery has taken place, 14% for clarity, and so forth. Habitat, lower food web, and then fish and shellfish. So we can see that there's some progress has been made in terms of getting recovery, but there's still a long way to go for a lot of these attributes. And then this is the last one. This just shows dissolved oxygen. And this is a fairly complicated graph, so I kind of like to torture you with it a little bit. On the x-axis is the year, and the y-axis is the total volume of water below 5 milligrams per liter of dissolved oxygen. So let's just look at the top of the bars here. Okay, if we skate across the top, that's the total volume of water that fits the hypoxia criteria. And you can see that it varies from, let's see, the lowest here, about 10 times 10 to the 12th liters up to about 16 times 10 to the 12th. And so the bigger this is, the worse it is, the smaller it is, the better. But you can see that from 1985 to present, there's no systematic trend as a result of instituting the Chesapeake Bay Program. However, very good quality monitoring. Now, if you want to say, well, how much of it is severely hypoxic, 0.2 to 2 milligrams per liter, then you would go across these hatched or like polka dotty bars, and that would be here. And if you want to see the basically the dead zone of the bay, you go the solid red bars at the bottom. So that's what this kind of stacked column plot shows. And the bottom line is that across all these different indices that I've shown you, that Chesapeake Bay has not recovered. However, what I hope the bigger message here is that we've got a monitoring program in place. There's a lot to do. You can see how important it is to have hydrologists looking at the water quality and how that interacts with different organisms to see what the overall health of the bay is. And of course, trying to come up with a rational strategy with equal effort sampling and being mindful of the different estuarian zones, recognizing that this is a coastal plain, lowland estuarian type, and figuring out for each goal that you have, having an appropriate monitoring regime for assessing that. Okay, so that's what I want to say about lakes and estuaries, and then we'll continue on looking at subsurface sediment and groundwater next.